have our former director, Professor Balasubramanian, and former director of CMI, Karantika, here. And I request Professor Karantika to introduce Professor Balu. Balu is, of course, known to all of us, and it's going to be telecast on YouTube and for those who do not know.
So welcome to this program, and yeah, it did feel strange that I should come at IMSC and introduce Professor Balasubramanian, or Balu as everybody knows him, but now a little bit of air is cleared because it's also live on YouTube and people who do not know him perhaps are listening. So for their sake, Professor Balu, I should say the leading number theorist in India at least for some decades now, and former director of IMSC. And I will just make one small anecdote that it is believed by many and probably true for several directors that once you become a director, you lose touch with academics, and because you are so much tied up with things, academic, non-academic matters and so on and so forth, especially when you go for meetings in Delhi. And I used to be in Delhi, and I met, maximum time I spent with Balu is when he used to come to Delhi, and after his meeting is over, we would be chatting away. And while we will be talking about this happened, that happened, but my office, one of my friends had written a question for me, okay? He had asked me and I had no clue how to do that, but he said, I'm leaving it here so that your free time, stare there and figure out what it was. And I don't know if Balu remembers, but one such thing, we were talking about other matters, about ISI, about IMSC, etc., etc., and suddenly he says, hey, what is that? I told him such and such problem. Unsolved? I said, yes. He said, okay. Next morning or maybe same evening, he was there with a full solution for my friend. So that is Balu that I know, and I suppose that continues. And I'm sure several of you would have stories of these kinds. So without taking any more time, let's listen to Professor Balasubramanian on number theory in India after Ramanujan.
Thank you for this invitation. In particular, I should thank the director for having asked me to give this lecture. And the list of acknowledgement, of course, is more, which probably I will talk about at the end of the lecture. Okay, we are going to talk about, is it clear or probably lights have to be? Yeah. We talk about number theory in India after Ramanujan. Okay. Okay, speaking about India in the period immediately following Ramanujan, the Chandrasekhar said, the facts of Ramanujan's life were more than enough for aspiring young Indian students to break their bonds of intellectual confinement and perhaps soar the way that Ramanujan did. Therefore, his life was having a great influence on the mathematicians and number theorists who were following him. But however, not many people do know who were the number theorists who were following him. Therefore, we trace the influence of Ramanujan by detailing the works of the number theorists of India following Ramanujan. And in fact, Bajji remarks, it's a little wonder then that the general public, including a majority of non-mathematical scientific community, finds it hard to name an Indian mathematician who made a mark in the world of mathematics after Ramanujan. And that's exactly what I plan to do, to really talk about the number theorists who followed Ramanujan and what is their contribution. And since once he's talking about number theorists, one cannot avoid mathematics. But on the other hand, one is talking to a general audience, therefore one cannot include mathematics, and therefore that was a dilemma, and I have sort of trying to balance between the two. A little mathematics, but not too much. The first person who we meet is Anandrao, and in 1914 he sailed for England, and only 4 months after Ramanujan. And actually he belongs to a family somewhat which can be called somewhat rich. and consequently he did not have to go through all that ordeals which Ramanujan had to go through, and therefore immediately after his college education he went. And even though he met Ramanujan for the first time in England, probably he would have heard of him before. Anandrao was a relative of Diwan Bhagavatar Ramachandra Rao, and Diwan Bhagavatar Ramachandra Rao was the one who got a job for Ramanujan in Madras Port Trust. And by 1916 he completed both parts of the Cambridge Mathematical Typos exam. It's Anandrao. He had his birth and early life in Chennai and studies in Presidency College, Chennai. I mean, the fact that he studied in Presidency College, I will talk about it a little later. And as I told, it was, even though he has not met Ramanujan before, but Ramanujan knew him through this Ramachandra Rao, and Ramanujan writes in a letter to his mother, நீ எனக்கு ஒரு சாமான அனுப்ப வேண்டாம், ராமச்சந்திர ராவுக்கு வரவு ஆனந்தராவ்ங்கிற பையன் இங்கே வாசிக்க வந்திருக்கிறான், அவரிடம் சேஷோயர் என்னென்னமோ சாமான்கள் எனக்கு கொண்டு வந்து கொடுக்கும்படி சொல்லியிருக்கிறார். That was a time more or less the First World War, and Ramanujan essentially writes to his mother, you don't bother to send anything now because it will not reach. But on the other hand, Anandrao is coming to study here, and Seshoyer has given something to be given to me, and I can manage with that. And as probably you know, Ramanujan was cooking his own meals, and he could not eat there, and therefore he definitely needed all the Indian curries for his meals. Now Anandrao finished Cambridge Mathematical Typos, and his first result was on summability. Summability was a favorite subject of Hardy. What does summability really mean? That it gives a meaning to an infinite sequence which may not be convergent in the usual sense. If it's not convergent, still you want to have some meaning out of that, and that's what summability, and there are lots of summability results in the literature. And in fact, most of the people, Hardy was interested in summability due to his influence. Most of the mathematicians in Chennai were working on summability. And Hardy had earlier proved that a sequence which is lambda k summable and has appropriate growth conditions is in fact convergent, but the proof had a little gap in it, and that's exactly what Anandrao did. He filled up the gap. And as the reviewer points out, that paper itself shows the clarity of exposition and attention to details. And again, on a theme related to summability, he wrote an essay under the supervision of Hardy and won the Smith Prize, and he was soon elected as a fellow of King's College. And then he returned to India in 1919 and became a professor of Presidency College, the same college in which he studied, at the age of 26. And then after coming here, worked on various aspects of number theory. His first paper from Chennai deals with the Hadamard factorization of s minus 1 into zeta s. Therefore, probably you can say that the first person who worked on zeta function from Indian soil is Anandrao. And even though this result was known earlier, Anandrao's proof was elegant. And in fact, according to K Chandrasekaran, about K Chandrasekaran we will see a lot later, that yields an alternative proof of Hadamard's theorem. And his other works include some questions of elliptic functions, in which again Ramanujan was also interested, representation of integers as sum of squares, and Waring's problem. This Waring's problem would be one common thread you will see throughout the lecture, and sometime I will probably even explain what the problem is. Anandrao established an excellent school in summability and Tauberian theory, and he invented all important number theories from South India. This includes S.S. Pillai, about whom I will talk, Thirukannavaru Vijayaraghavan, Kumaravelu Chandrasekaran, and I have put Meenakshi Sundaram separately because Meenakshi Sundaram also is an equally great mathematician, but I am only talking about number theorists, and Meenakshi Sundaram did not work much in number theory, and therefore I am putting it separately. But Pillai and Vijayaraghavan and Chandrasekaran were all number theorists. Good. Now I want to talk about Pillai. And before Pillai, I think, now unfortunately I cannot avoid mathematics completely, therefore let me say some mathematics for the Pillai's work. Hardy and Ramanujan were interested in the question, given an integer n, what is the expected number of distinct prime factors of n? Is that even an expectation that lies? Already lambda has shown that for a given k, how to count the number of integers having exactly k distinct prime factors. I mean, if you want to count how many numbers have k distinct prime factors, he has counted. And Hardy and Ramanujan realized that instead of this asymptotic formula, if one can get even an upper bound, but not for a fixed k, but a k going to infinity, then they can solve this problem. How is the expected number of distinct prime factors? And that's exactly what they did. Can I have some water? Yeah, that's exactly what they did. That they actually got an upper bound of the expected order. And in fact, they proved that almost all integers have around log and prime factors. And Paul Turan gave a different proof, and that gave to probabilistic number theory. That's a different point. And now we come to Pillai. Pillai had an early education in Nagarkoil, Tamil Nadu at the Thiruvananthapuram. He joined Anandrao University, and he was also a student of Anandrao, as we saw earlier. And he was the first DSc for Madras University. And then he stayed for a long time in Anandrao University, which is 1929 to 41. And after a stint at Travancore, he went to Calcutta. That is in 1943. And in 1950, he was traveling by flight to attend the International Congress for Mathematicians, and then he was planning to spend a year in the Institute of Advanced Studies. But unfortunately, his end came when the flight crashed near Cairo on August 31, 1950. And therefore, he sort of died young, and he was a very prolific mathematician, did fantastic things, but unfortunately we lost him. Okay. Now Hardy was interested in the following question: how much you can get an asymptotic formula? For which range of k can you get an asymptotic formula? Lambda has already got it for finite k, and Hardy wanted to know as k goes to infinity. And that is the one about which there was a beautiful article by Yardash in Annals of Maths, and he says Hardy and Ramanujan proved pi kn is less than c into n into log by log n power half. And Hardy conjectures that that is also true, which means that you are now taking your x to be around log n. It's not a constant anymore. And then Yardash continues. Pillai had proved the conjecture independently. And the most important point is the last but one line. I believe a formula like 4 holds for k less than cx, but the proof presents difficulties which I have not yet been able to overcome. And that is exactly what Pillai did. That whatever problem we understand, he was able to prove for k around log x, but he wanted to go a little more than k log x, and that's what Pillai did. And of course, it was not Pillai, more precisely. In Calcutta, Pillai suggested this problem to his doctoral student Sathya, and put at Sathya's disposal all of his manuscripts on this problem. And Sathya solved the problem in less than 2 years. That was his PhD. Yeah. And proved that Landau's asymptotic holds for k less than e log n. It should be log, not log n, sorry. In particular, he solved the Hardy's problem completely. And the proof is rather a long proof, running to 134 pages, which appeared in Journal of Indian Math Society in 4 parts. Okay, in number theory, a proof is called elementary if it doesn't use complex analysis. And elementary proof does not mean a simple proof. Most of the time, elementary proofs are more complicated proofs. Okay, and it's called analytic if you are ready to use complex analysis. That is essentially because in the earlier periods, complex analysis was considered one of the very difficult subjects. And therefore, if there is a problem and if you can solve it without complex analysis, why not? Then that is called elementary. And that became essentially famous because of prime number theorem. Prime number theorem says how to count the number of primes up to some capital N. And if you want to count the number of primes up to capital N, the only method that was known was to use some complex analysis and something called Riemann zeta function. But the problem has nothing in complex analysis. It's a counting problem. It's a problem in real analysis. As a problem in real analysis, you would expect, of course, a proof in real analysis. I don't say you need a complex analysis at all. And that's where can there be an elementary proof of prime number theorem, which means a proof which does not use any Riemann zeta function, proves only using real analysis. And that is what Erdash and Selberg did independently. They produced a proof of prime number theorem without using any complex analysis. Sathya starts with the prime number theorem and gives an elementary proof. That elementary proof is a very complicated proof, as we saw 134 pages. Therefore, this elementary and complicated thing. And there is a referee report in Selberg says, while the results of Sathya's paper are very beautiful and highly interesting, the way the author has proceeded in order to prove the result is rather a complicated and involved one, and this by necessity, since a proof by induction after V starting from the case V equal to 1 presents overwhelming difficulties in keeping track of the estimates of the remainder terms in the dependence of the two parameters V and X. And then of course Selberg wanted to see whether this problem can be done by analytic method, complex analysis, and he had to give a simple analytic proof in 5 pages, which appeared immediately after this paper of Sathya. If you look at the Journal of Indian Math Society at that time, there will be this paper of Sathya followed by the paper of Selberg. And this is now known as the Selberg-Deligne method and turned out to be a very powerful tool in analytic number theory. And now since I talked about the variance problem, let me just say a few things about the variance problem. We want every integer to be sum of s kth powers. And then you ask what is the minimal number of summands which you need. Call that number Gk. And Hilbert proved that this number is finite. And Lagrange proved, for example, G2 equal to 4. Every number can be written as sum of 4 squares. And in fact, if you write a program for determining the number of summands, you will see a pattern. Okay? Normally you would expect that probably bigger numbers will need lot of kth powers and smaller numbers will need less kth powers. But in fact that is not so if you write a pattern, simply because the smaller numbers do not have many kth powers to play with, whereas the bigger numbers have lot of kth powers to play with, and consequently the smaller numbers is the one which needs lot of kth powers. In fact, how many you need? Take 3 power k divided by 2 power k, and therefore 3 power k equal to q times 2 power k plus r, and you consider the number q times 2 power k minus 1. And this number is less than 3 power k by definition, because 3 power k is q times 2 power k plus r, and therefore you cannot even use 3 power k because your number is 3 power k, and therefore you can use only 1 power k and 2 power k. You don't have many choices. Since you have only 1 power k and 2 power k, essentially you will find that you need q plus 2 power k minus 2 summands. And therefore the variance problem can be probably conjectured as the number is q plus 2 power k minus 2, where q is the quotient when you divide 3 power k by 2 power k. And that's exactly variance problem. And in fact I rated A and B because even variance gives only A. He says G3 equal to 9, G4 equal to 19, and so on. He does not give the value for Gk for general k, and that was given later. And Hilbert's original method was combinatorial. It proves Gk is finite, but does not lead to any decent bounds. And Hardy and Littlewood used a circle method to attack the problem. The method is in fact a variation of another method used by Hardy and Ramanujan to get an asymptotic formula for the partition function, and that question itself is a variant of a particular problem which Ramanujan writes to Hardy in his first letter. Therefore everything finally you trace to Ramanujan, and this method was later defined by Davenport, Vinogradov and others. And using this method, Pillai proved a remarkable theorem and therefore finally settled what is the Swearing's problem. And he proved that if k is at least 6, then the gk is either the expected value or maybe one more. Either the expected value q plus 2 power k minus 2 or maybe one more. And in fact he also gave an algorithm to decide for each k whether it is the first case or it is the second case. And therefore once you have an algorithm, therefore you know the exact value now. Okay, you have to just put the algorithm to see whether it's the first case or second case. Okay, therefore Pillai had a lot of works, since I don't have much time, but he is very famous for these two works. One by himself on Swearing's problem and another by his student Sathya on number of numbers whose prime number which they have exactly k prime factors. And the next person who I want to talk about is S.D. Chowla. He was born in London, brought up in Lahore, and he finished his PhD under the supervision of J.E. Littlewood. And most of you would have known J.E. Littlewood was the collaborator of G.H. Hardy. And he immigrated to USA in 1948 and never came to India again. And in fact, when I was in Princeton, I used to talk to him, and then I used to ask him to come to India at least once, but he never did it. Among the persons Chowla thought, mention should be made about R.P. Bamba, who probably most of you will know, he was even the Vice Chancellor of Punjab University, F.C. Aulak, Abdul Majid Main, and Abdul Salam. Okay, there has been a regular correspondence between Chowla and Pillai for 20 years. You see, that is the time when, of course, there was no email or any such a thing. You have to only write the letters. And the only thing which they will do is to wait for a conference. And the conference normally would mean the annual conference of Indian Math Society. And where, therefore, all the mathematicians would go there so that they can meet their friends and so on and so forth. The possibilities and the chances of meeting the friends were much rarer those times. And only these conferences you have to do. In his first letter, Chowla remarked that something is the sum of two positive cubes in three different ways. This is one of the problems of the taxi cube problem of Ramanujan which you would have seen. He ends a letter by expressing the hope that they would soon begin their proper work, and they did it. Their first paper in 1930 was on the summatory function of Euler's phi function. And they obtained something called omega results. Omega results meaning that when you have a summation of a certain function, you have a main term and then the secondary term. And then when you want to say that the secondary term is small, that is called O results in number theory. But if you want to say that the secondary term is not very small, they are called omega results. Therefore, in omega result means the secondary term is not very small. And in fact, their method of obtaining the omega result for this phi function remained the best until around 1987, till Professor Montgomery came with a different idea of how to improve those estimates. The second theme of their work deals with the Pell's equation, x square minus n square equal to 1, and this was extensively studied by Brahmagupta and Bhaskara at 2. Pillai and Chowla investigated the length of the continuous fraction. And Chowla is well known for many of the theorems. Is the Bragg-Reiser-Chowla theorem, Ankeny-Artin Chowla congruences, Chowla model theorem, Chowla-Silver formula, main Chowla sequences. And the next person who want to see is Thirukkannapuram Vijayaraghavan. Thirukkannapuram Vijayaraghavan had many similarities with Ramanujan, even though of course he was not poor, he was reasonably rich, but other than that he had many similarities. For example, like Ramanujan, he did very well in school, but not in college. Essentially again, like Ramanujan, due to his preoccupation with mathematics, he was spending all the time with mathematics. And spotted by Anandrao, and this is a comment which I think Professor Raghavendranath makes in one of his articles about Vijayaraghavan, that Anandrao was very clever in really seeing who are the best people, because with his marks that he obtained, he could not have got admitted in BA honors. And it was Anandrao who said that he is intelligent, he has to be admitted, and therefore thanks to Anandrao he got admitted in BA honors. And exactly like Ramanujan sent his research papers to Hardy and then sailed to England to work with Hardy. And then when he came back, he started his professional career in Aligarh in 1930 at the invitation of Anandrao. And probably most of you would have known that Anandrao did work in India around 1930 for 2 years in Aligarh Muslim University. And then afterwards something happened which we will not discuss. Anyway, he decided to resign and he moved to Dhaka because that's where Chowla was there. And then finally came to Chennai, and that is the time the Ramanujan Institute was started, because definitely people thought that there has to be an institute in the name of Ramanujan, and it was a philanthropist who started the institute called the Ramanujan Institute. But unfortunately then it went into certain financial troubles, and therefore the institute was taken over by the Madras University as its mathematics department, as most of you would have known. But now the time when I am talking is, it was not a part of the Madras University, it was an independent institute. And then he became the director of that place. And again his main contribution was on summability, not surprisingly, and definite approximation. And he has a great work on definite approximation. He also worked on some questions in analytic number theory. That is essentially because of the influence of his friends Chowla and Pillai. And he is known for a disproof of a conjecture of Borel on the solution of nonlinear differential equation. And there is again one term in his name, let Px be a monic polynomial with integer coefficients with exactly one root outside the unit circle and all the other roots inside the unit circle. And that root which is outside the unit circle is called a Piso-Vijay-Raghavan number, because this particular number comes in the study of the uniform distributions of alpha power n, which was started by Hermann Weyl. That ends the first epoch, therefore I have just taken half an hour. With the immigration of Chowla to abroad and debates of Pillai and Vijay-Raghavan, we enter the second epoch of number theory in India, where Tata Institute plays a major role. You see, individually the individual people were working, but on the other hand, having an institute, having a lot of people there, it always gives a different advantage for the people, instead of each one individually working. And these are the people who we are going to talk about. The first is Kumaravelu Chandrasekharan. Kumaravelu Chandrasekharan was born in Machilipatnam in Andhra and had his studies in Bapatla, and he is finishing his MA Maths from Presidency College, again under Anandrao. Okay, when you go and talk about Kumaravelu Chandrasekharan, as again you should remember, was a first-rate mathematician, a top mathematician. But on the other hand, when you go and talk to anybody about Chandrasekharan, their first reaction would be, he is a great institute builder. I mean, he brought that mathematics department of Tata Institute to a great height. And since that is not the main topic of this, let me just mention about that for a couple of things and then go to the mathematics. In the year 2003, TIFR brought out a booklet titled Some Famous Scientists. And there they had J C Bose, V C Ray, Ramanujan, C V Raman, Saha, etc. And the comment about KC which was made was, his achievements are first rate, but his contribution to Indian mathematics has even been greater. For example, this is what Seshadri has to say on KC. A man of intellectual humility and integrity, whose striving for excellence helped the School of Mathematics of TIFR gain the reputation of being a world-class center for mathematics. And then CSS also says the following: when he went to France and made quotes for the first time, the first comment which quotes made was apparently, how did you manage to do it? How did you manage to bring a world-class mathematical institute in India in such a short span? Is what quotes have simply asked. And Actually, I met Coates around 20 years back in London, and then I told him to, can you come to India? And he said, I don't need invitation, Balu. You Seshadri calls me and says, come, and I will come there, type thing. That was the way the Seshadri was actually teached by others. And this is what Casey says about Nancyman. In the span of 15 years, Casey set up an institute in India which was soon recognized internationally as a leading center of research in mathematics. His extraordinary gift for organization and administration, his leadership qualities, and his complete devotion to mathematics made this possible. This is exactly what Nancyman says. And I consider the School of Mathematics of TIFR is a remarkable achievement, and it is without a parallel in any other country. That is what Schwartz says. And now Weil writes various things that the mathematics in India at that time when he came was not that great, and so on and so forth. And then says, since then, as one knows, this has changed due to the creation of TIFR. Therefore, I mean, his institution building, his bringing TIFR to a high place, I mean, that was a major achievement by him, even though he is a first-rate mathematician. And we are only going to talk about his mathematics, which was done in India, not before he came to India or not after he left India. And those mathematics were done in collaboration with a person by the name of Raghavendranath. And therefore, let me talk about the Raghavendranath also and then go to the mathematics. This Raghavendranath, he completed bachelor's from Loyola and he got his PhD in 1963, 26 years old. And the reason why I am saying that he got his PhD in 1963 will be known a little later. Yeah. Then he was in TIFR, he was in Institute of Advanced Studies and in Geneva, and then finally settled in Chicago, University of Chicago. And he became famous for solving Levy problem in complex spaces and was invited to ICM 1962, which was 1 year before he got his PhD. Therefore, he gave a lecture in ICM 1 year before he got his PhD. Nancyman was an analyst. He was a top analyst whose work has technical virtuosity, breadth of vision, and elegance that in difficult technical fields like analysis are hard for non-analysis to appreciate. And Nancyman had a truly astounding insight on analysis, is what Madhav says. And he had an unusual memory for taste. He could drink a wine in 1990 and 10 years later drink the same wine and describe how it has changed. Okay, now we want to talk about the mathematical work which Casey and Nancyman did. Hamburger had already proved that the functional equation for the Riemann zeta function determines the zeta function uniquely. This is one of the recurrent themes at that time, and which was not pursued for some time later, and then now Perelli and Kaczor again started this theme, and this is an important theme in number theory. And Casey and Bochner studied the number of linearly independent solutions of a pair of Dirichlet series satisfying a Riemann type functional equation. One of his other results is Hardy and Littlewood had obtained the approximate functional equation for the Riemann zeta function. I mean, I don't intend to explain what a Riemann zeta approximate functional equation or something like that. As well as for the square of zeta also they got the approximate functional equation. But Casey and Raghavendranath showed how to obtain an approximate functional equation for any Dirichlet series having a functional equation. Therefore, if you have a functional equation, you always have an approximate functional equation is what they showed. And then Casey and Nancyman developed a method in Analyst 1962 for getting the Riesz means under the general conditions. And this method has been extensively used by later authors to get the average order of arithmetic functions whose generating functions satisfy some zeta functions with multiple gamma factors. And the next person who we will talk about is K. J. Ramanathan or Kollaguntu Gopal Iyer Ramanathan. He was MA from Madras University, PhD from Princeton under Emil Austin, and joined TIFR in 1951, and along with KC, he brought a great school in TIFR. His earlier papers dealt with, for the most part, with the congruence properties of some arithmetic functions, Ramanujan's trigonometric sum, certain identities of Ramanujan type. I mean, that was traditionally the Ramanujan type work. He was well recognized for his achievements in number theory, especially the analytic and arithmetic theory of quadratic forms over division algebras with the involution. The next person who we will talk about is C P Ramanujan. I mean, when I say C P Ramanujan was a number theory, there could be some objections. Therefore, let me explain what the objections could be. This Chakravarti Padmanabhan Ramanujan, he studied in Loyola College, and the Loyola College produced many students for TIFR, and that is due to Father Resin, and the contribution of Father Resin in that is probably a different story to be told in a different date. And he cleared both the ISI entrance exam as well as TIFR entrance exam, and decided to choose later. And apparently his father was not very happy with that, because he has never heard about TIFR, but he has heard about ISI, and said that once I got in ISI, why did you go to TIFR, why not you join ISI? But anyway, he joined TIFR. In the old tradition, this is what really Chandrasekaran made. He would invite great people to give a course of lectures, because there was nobody in India to give any great lectures, and then he would ask the students to write the notes for it, and that is how the students learned the subject. Once you have to write the notes, you should know really what the subject is all about. And the first year he took the notes, the very first year, he has just joined, and then of course Max During was there. He gave a lecture on algebraic functions of one variable, and he took notes of that. And then there was this lectures by Sheferovich on medieval models, and which Ramanujan took the notes, and about that Sheferovich makes a comment. Ramanujan not only corrected my mistakes, but complimented the proof of many results. And he also took the lecture notes of abelian varieties by Mumford, and Mumford says, this work is really a joint effort between me and Ramanujan. Okay. Therefore, not only taking the notes means just whatever they say, but he really improvised the material, so that whoever gave the lecture was very well appreciative of the way finally the book came. And for his thesis, he worked with K.J. Ramanathan, and this is his thesis problem, which is the number theory, because K.J. Ramanathan was a number theorist. Let K be a number field. C is a homogeneous cubic form with the coefficients in the number field K in m variables, and if m is large, one would expect that C has a non-trivial zero in K. And it was known only for the field K equal to Q, rational field, which Davenport proved that if you have 29 variables, it's good enough. Anything which is more than 29 variables will have a non-trivial zero. And people expected that probably a similar thing should be true for any number field. Probably the constant may depend upon the number field, but other than that, it should be true. And what Ramanujan did is, irrespective of the number field, 54 variables is good enough, which was considered as a great result, because whatever Davenport did, he improved in such an unexpected way. They didn't even expect that you will be able to get a constant which is independent of the number field. The same thing which he did with Waring's problem. In an article in the American Journal of Mathematics, Siegel considered the following generalization of Waring's problem. About Siegel I will talk a little later. Let K be a number field of degree n, let R be given. For any m in K, write m as sum of rth powers, which is exactly the Waring's problem we saw. We have to write the number as a sum of rth powers. But the fact is, unlike the case of Z, it may not be always possible. Therefore, you have to make some assumptions so that it will be possible to write. This is not always possible, but we assume m is totally positive, m is in the order generated by rth powers, etc., so that you can really write the m as a sum of rth powers. Then what is the minimal S for which every m can be written as sum of s r to the power s. That's corresponding to the gk in the variance problem. What is the minimal number? Siegel proved that at least 2 power r minus 1 plus n times nr plus 1 will do. And then writes at the end, the question arises whether the lower bound could be replaced by a function of r alone. However, the solution of this new problem seems rather difficult. And that's exactly what Ramanujan did. He got something which is a function of r alone independent of n. And it is told that on the basis of these two great results, because one was an improvement of a result of Davenport and another was actually an improvement of a result of C.L. Siegel, which anybody would be proud to have even one of them. And because of that, he was promoted to a professor, and he was unhappy of being promoted. He said, I do not deserve it. I mean, to become a professor, one has to do more, and therefore people had to convince him, no, you should become a professor type thing. And therefore, after much convincing, he decided to accept the professorship. But then the point is, when I told you why I didn't call it number theories, first of all, that these two papers already would really make him comparable to any other number theorist in India. I mean, two great papers. But however, then since he was writing the notes for other lectures, he was somewhat attracted by algebraic geometry and then decided to move to algebraic geometry, and where his work in algebraic geometry seems to be of a much higher level even compared to his work on number. His work on number theory is of a high level, but then later his work on geometry was on a much higher level that people sort of recognize him more as a geometer than a number theorist. And then finally I come to Kanakanagli Ramchandra, and that about him only I will talk, and that was stopping. And he studied in Central College, Bangalore, and again he was somewhat poor, and his father died somewhat young, and therefore he has to take care of the family. Therefore he could not immediately join Tata Institute after his education. For 1 year he worked and then joined Tata Institute, and his thesis gate was K Ramanathan, whom we saw, and the thesis problem was suggested by Siegel. Again let me say that is the time C.L. Siegel was giving a course of lectures in TIFR. Okay, because he was, as I was telling earlier, KC expected KC wanted all the for mathematicians to come to India and give course of lectures, the students take notes and so on and so forth. And then Siegel was giving a lecture, and then Siegel suggested the problem. And then he did this problem. He started his career with a bang because his thesis was on some application of Kroneker's limit formula. This was the problem which was suggested by Siegel. It appeared in Annals of Mathematics. So you start with that, your first paper appearing in Annals of Mathematics is in no mean achievement. In his thesis, he deals with the three problems: construction of Ray class fields over imaginary quadratic fields, construction of maximal system of independent units, the values of a modular form and its derivative when the argument takes values in an imaginary quadratic field. And the problem C has some connection with some Ramanujan's writing. I don't have time to do it. And in 1970, H.M. Stark was giving an ICM talk, and he makes a conjecture and remarks, unless I have missed something, the proof is a simple matter of deciphering the notation of Ramachandra and applying his result. I mean, he was a great researcher. He did some great work. But one cannot call he was a good communicator. I mean, one had some difficulties in trying to understand what he was trying to say. And then, therefore, in some algebraic number theory, he proved great results. And after proving some 2 or 3 great results, he got bored and then decided to change his subject. And that is the time when Alan Baker proved his famous results on what is called the linear forms in logarithms. This lower bound was improved by many mathematicians, including Ramchandra, and this is called what is called a transcendental number theory. and it is the time he proved another result called 6 exponential theorem. And Ramachandra was also interested in the applications of Baker's theory for arithmetic questions. Therefore, let me give one example. Suppose you are given an integer n, and we are interested in the maximum value k, such that every integer j in the interval 1, 2, 3, etc. up to k, one can find a distinct primes pj such that pj divides n plus j. Therefore, I want k distinct primes p1, p2, etc. pk such that the jth prime will divide n plus j. How long can you take it? The original conjecture says this holds if all the numbers are composite. And the best result known is due to Ramachandra's Chowla Pillai. I mean, Chowla was one of his brilliant students who joined Ramachandra around the time, probably the best student of Ramachandra. And in 1976, and they proved that the conjecture holds if k is less than constant times log n by log n whole cube. Even though the result is probably weak, in spite of many attempts, no improvement of the result is known for the last 50 years. And then, of course, he got bored in transcendental number theory. He decided to change the subject, and then he did something on sieve theory, and then something on Dewey-Roth theorem, and then somewhere around 1973, he decided to study Riemann zeta function, and then there was no going back. He continued on Riemann zeta function till then. He proved many remarkable results in the theory of Riemann zeta function. We will give an example. His results on the upper bound for the fractional means of the zeta function were more or less the first results in this direction. And he, with his collaborator, developed a method in 1980s for finding a lower bound for the L2 norm of Dirichlet series in short intervals, and used this with the collaborators to prove omega results for the summatory function of arithmetic function. And one of the omega results was proved by Schinzel, and Schinzel writes in his article, he considered summatory function of something called Rn whole square. Rn is the number of ways of writing the n as a sum of two squares, and he writes, as far as I know, there is no omega result in the literature, and it is the aim of this paper to prove such a result. The proof is based on the approach of Ramachandra. Therefore, essentially, that was the only idea which was used. And in fact, for a long time, this idea of Ramachandra remained as the best method for getting omega result, till around 10 years back, Soundararajan came with his resonance method, which gives a better result in many cases. Earlier, Ingham showed how to prove the non-vanishing of the zeta function on the one line without using an identity, without using this 3 plus 4 cos 3x plus cos 2x idea, but just using an identity of Ramanujan. Ramachandra, his collaborator, showed how to use this idea to get a zero-free region. And this idea also turned out to be rather powerful. In fact, let me quote from a recent paper of Peter Humphreys and Brumley for obtaining standard zero-zero function for the Rankin-Selberg L functions. The method of proof is of particular interest. It is essentially a generalization for GL1 of AQ. This is what Ramachandra did to GLN of AF by the method of Ramachandra. I think it is time to stop. Therefore, let me make two comments. Some of the slides have an overlap with the lecture I gave earlier, because this lecture, every time I keep on improvising it. I started in 2010, and I thought at least I should publicize the number theories in India, and I have gone for 3-4 times, every time improvising a little more, etc. And in particular, the more mathematically oriented, I wish to take my ICM talk where I have given all the mathematics also. And coming back finally to acknowledgement, I should also thank Ajit Samal for having invited me to give this lecture, and he and his team for the various other helps which they did, which he explicitly forbade me from mentioning. And with that I will stop.
Any questions or comments that you like Subramanian to address?
Yeah.
Can you say something about Father Racine?
Oh, you want to say something about Father Racine? Okay. Father Racine was working in the, Father Racine is a Jesuit, was father from France, and he worked in France and with a great PhD thesis and knew all the French mathematicians, and then decided to come to India, and I think probably for some time he was in Trichy and then moved over to Loyola College in Chennai, and according to the reports, he is a good mathematician, very good mathematician, but he cannot be considered top, and probably a very good teacher, but again I cannot be considered top, but on the other hand was very interested in identifying people who are very good, giving them the special training, and then asking them to go to an appropriate places where they would be able to continue the things. Particularly, he was mainly responsible for many of the people going to TIFR. This includes Professor Seshadri, Professor Nancyman, CP Ramanujan, and not Raghavendranath. Raghavendranath is from Vivekananda College. These three people are from Loyola College, and Raghavendranath is from Vivekananda College. And Anandrao Swarup. And many people, I mean, at least the 4 people I know. And yeah, he was very instrumental in identifying the people. I mean, this is something which we saw in the case of Anandrao also earlier, that he was able to identify the Vijayaraghavan. And for his mark, Vijayaraghavan would not have gotten admission, and he was able to identify, said that he will become a great mathematician, etc. And that capability even the Father Racine had. I probably TRG may be able to say more. Yeah. Sorry?
Even after the last, his name was always.
Yes.
Did anyone come before to go to
Sorry?
Did anyone come?
One hears a lot of talk on that thing in the tea tables, and I do not know whether it is proper to make any comments at all based upon the tea table talks.
Any other comments? It's not next time for the
The historical aspects, to those of us who did not know the entire history, who all contributed when and where, so that's thanks.